Welcome to The Explainer. Today, we're going to dive into a pretty revolutionary idea from over 50 years ago. It's not to answer a huge question. How can we actually prove that our software is correct? To really get why this idea was so powerful, let's start with a problem that, honestly, every single one of us has experienced. It doesn't matter if you're a programmer or just trying to use your phone. I mean, just think about it. We rely on this incredibly complex code for everything. Banking, flying planes, you name it. It's like the invisible architecture holding up our modern world. But with all that complexity, how can we actually trust it to work correctly every single time? And we all know this intuitively, right? From those minor little glitches in an app to, catastrophic system failures. Bugs are this constant reminder that writing correct code is just incredibly difficult. For decades, the main way to handle this has been testing. But here's the catch. Testing can only show you that bugs are present. It can never prove their complete absence. So, this fundamental problem is what led the brilliant computer scientist C.A.R. Hoare to propose a really radical shift in thinking. He asked, what if we could approach programming with the same kind of rigor that we use in mathematics? This quote is just so powerful because it completely reframes the whole act of coding. It's not just a craft, it's not just a set of instructions. Hoare was arguing that no, this is a rigorous logical discipline, and it should be subject to the same rules of proof as any mathematical theorem. His vision was, ambitious. He wanted to build programs that could be proven to meet their specifications before they were ever even run. Much like an engineer uses physics to prove a bridge will stand, a programmer could use logic to prove their code is correct. No more guesswork. Okay, so how did he propose to do this? The answer lies in the central tool he created, a structure that is just brilliantly simple and elegant. Now, to understand Hoare's method, it helps to know there are different ways to even define what code means. His approach, which is known as axiomatic semantics, isn't so much concerned with the machine's step-by-step execution. Instead, it's all about the logical assertions, the things we can prove to be true about the program's state. And this is it, the Hoare Triple. The entire system is built on this one elegant concept. It says, if the precondition P is true before you run the program Q, then the postcondition R is absolutely guaranteed to be true afterwards. Think of it like a formal contract for a piece of code. Let's use a simple analogy, a recipe. The precondition is your starting ingredients. You have eggs and flour. The program is the instruction, mix them together. And the postcondition is the guaranteed result. You now have batter. See? If you start with the right ingredients and follow the instructions, you're guaranteed a specific outcome. Okay, that's great for one line of code. But how do you scale this up to an entire program? Well, that's where these individual triples build into something truly powerful. This is what's known as correctness by construction. Instead of writing a whole program and then testing it for bugs at the end, Hoare Logic lets you build a proof of correctness from the ground up, line by line as you go. You basically create a logical chain. The postcondition from the first line of code, the thing you've just proven to be true, becomes the precondition for the second line. And then that line's postcondition becomes the next line's precondition, and so on and so on. This approach lets you prove that if your initial assumptions are true, your final result will be correct. Guaranteed. Now, this idea had a massive impact on computer science. But like any powerful system, it's also really important to understand its boundaries and, of course, its creator's broader legacy. I mean, Hoare's work was way more than just this one idea. He developed CSP, which is a foundational model for how systems do many things at once. He was a key figure in the Verified Software Initiative, and he fundamentally changed how computer science was taught, grounding it firmly in mathematics. This all leads to a pretty crucial question, though. When you're talking about any formal proof system, can it really be perfect? Can you really prove everything about every single program? Well, the answer comes down to the difference between two key concepts, soundness and completeness. Hoare logic is sound, and that's fantastic. It means if you prove something with it, that proof is trustworthy, it's actually true. That's absolutely essential. However, no system for complex programming languages can be fully complete. This is related to Gödel's incompleteness theorem. It means there will always be true things about a program that you simply cannot prove within the system. But the key takeaway here isn't failure, it's about focus. So we can't prove everything? Fine. But what we can do is use these mathematical tools to formally verify the most critical parts of our software. And by doing that, we can dramatically increase its reliability and our trust in it. And that leaves us with a final thought for the future. As code gets more and more complex, and as it's increasingly generated by AI, our ability to just read it and test it is shrinking. In a world like that, are Hoare's 50-year-old ideas about mathematical proof maybe more relevant than ever? Could this be our only real path to trusting the code that runs our lives?